I love the fact that when you develop really novel AI techniques, that you can apply it to so many different areas.
You're listening to Gradient Descent, a show where we learn about making machine learning models work in the real world. I'm your host, Lucas Bewald. Richard Socher was the chief scientist at Salesforce, where he oversaw development initiatives like Einstein's Cloud AI. As a PhD student at Stanford University, Richard helped create the ImageNet dataset and also founded the startup MetaMind. Recently, Richard left Salesforce to create his own startup, Susi, which is on a mission to build better internet using the latest NLP and AI technology. I'm excited to talk to him about all these things today. I was curious how you got inspired by this AI Economist paper and project. I mean, I was trying to read it, and I'm not an economist, so I had a whole bunch of basic questions that are probably pretty embarrassing. But when did you learn so much about economics? And it's such an interesting idea. Like, I guess maybe you should probably summarize the paper first for those who haven't read it, and then talk about how you got interested in it.
Happy to, yeah. So AI Economist is essentially a framework. It's more than just a single model or something. It's a whole framework that tries to model an economy in its sort of most simple forms for now, though it'll get more realistic, I think, in the next months and years to come. And then inside that economic simulation, you have a two-level reinforcement learning setup where you have an AI economist that basically can set taxes and subsidies and other kinds of financial instruments in order to optimize an overall objective for the economy, namely, in our case, productivity times equality, where equality is measured as sort of a 1 minus Gini index, which is a measure of equality that's used worldwide. Mm-hmm. And productivity makes sense in terms of how much do all the single agents in the simulation make. And each single agent is also a reinforcement learning agent, but their goals are just to maximize their own objectives, which is to maximize their own income and wealth. And, is that 100% realistic? Of course not. Also in the simulation, there's mostly just three different types of resources: wood and stone and space in some ways. And then agents walk around in this 2D world, grid world. They can build houses. They can block other agents by building these houses. And they can trade resources as well to try, if you need certain more wood to build the house, but you have plenty of stone, you can trade it and so on. So sort of some of the fundamentals. Also, you have utility curves, which is quite common in economic modeling that you wouldn't have in a game. What does a utility curve do? It tells you, for instance, that after a certain amount of work, you have diminishing returns. Like you could work 7 days a week, but most people at some point want to actually take some time off and not spend all their time just to minimize another little bit of money. And so that and a couple of other things make it quite different to playing just a game. We thought about this too. Could we just use Civilization or Age of Empires or some of these things? But we wanted to, steer away from just zero-sum war games where you train AI to just get really, really good at fighting each other, and instead try to think of a system to try to have an overall improvement for the world, so that if that system actually gets deployed, it would have as is a positive impact versus, we used it to develop interesting technology that eventually maybe will have this positive impact. And so that's kind of what AI Economist is. And what's interesting technically and hard about it is that with this two-level reinforcement learning, the AI Economist keeps changing the goalposts for all the RL agents. And they say, I found this great strategy. I'm going to, sell this, trade this, collect this resource and build houses in this way to block off some other person. And then all of a sudden the AI Economist changes it because they realize you have a monopoly and equality is suffering. And maybe you're going to tax the person with the monopoly a little bit higher who blocked all the resources away from the other agents. And now all of a sudden the agents have to adapt too. And in almost all RL before, you have a fixed objective function. This is what you need to fit. This is how you win Go. This is how you win chess. This is how you win Atari games and so on. They don't change. And here the goalpost keeps changing. So it is a really hard, interesting optimization problem. So that's kind of what AI Economist is. Now, how did we get to that idea? It actually came from a couple of different strains. The first time I had this idea was during my PhD, where I had this idea of essentially all these different cultures in the world have had there are different energy landscapes on their optimization strategy. And a lot of them are trying to optimize roughly similar things you would hope. People want to prosper, people want to have certain amenities and freedoms and so on, but they all end up in their different local optima. And I thought about this as like this non-convex objective function that different cultures go in and try to optimize it and end up in all these different local optima. And so that was kind of idea, but I didn't quite know how to structure it as like an AI problem. I just had some sort of quick little notes and I drew some objective function and I kind of just carted it and I continued to do NLP research. And then we hired Stefan Cheng, the first author of the AI Economist. And we've also had Alex Trott in the team already for a year. And with him, we were working on trying to build houses just from like lots of bricks. You collect resources and you have a 3D agent in like something like Minecraft that tries to build a house. And that house building turned out to be pretty complicated. But the goal of that house building project was to eventually have multiple agents and a whole island and like the whole thing. And then we realized, man, we could spend another 2 years or so or 3 years just trying to build the houses properly before we could get to that AI Economist. So I thought with Stefan, like, hey, why don't we just go directly, assume the house building is just one action, build the house in this location, and that's it, rather than all the different 3D structures and so on and finding out what is a good structure for a house. Just one click. And then eventually maybe we can merge the two projects. But then, yeah, Stefan actually did a phenomenal job deepening our understanding of the literature and economics and reached out to other economists. That's how we worked with David Parks in the end from Harvard, and really fleshed out how to make it work in an RL framework, and then getting all the technology, like the complex optimization going and so on. So I have to give a lot of credit to Stefan. And Alex eventually said, screw this simple house building. This is why I'm kind of wanted to do this anyway. And he's been interested in economics for a long time too. So the two of them kind of just jumped in on that project and it became really, really great.
That's so cool. Was there a debate over I thought there's actually a lot of kind of, could be a lot of debate in the objective function, right? You did the like economic growth times 1 minus the Gini coefficient. Why not like economic growth like plus the 1 minus the Gini? Or, I could think of many other ways to do it. Was that?
And so could we. And I think eventually you're going to I love this project in that it literally covers the whole spectrum from like a hardcore optimization problem that's really technical and sort of min-max and shifting objective function and energy landscapes and so on, all the way to the most philosophical civilization level debates and questions of what we need to do in the world and what is economics and politics and what are we all optimizing and should it be equality? Like in some ways you don't want the Gini index to go all the way to its maximum either, because that means sort of there's absolutely everybody's forced to be 100% equal, which is questionable.
Not a danger that these days.
Right, which is questionable in terms of monetary things. Of course, we should all be equal in terms of rights and opportunities and so on. But in terms of financial equality, it's very important. Thanks for pointing it out. Yeah, and in fact, I think actually this kind of work will help with that kind of equality because we can push for that and improve it a lot. Does it mean we have to get to the maximum, right? Like maximum would be like infinite productivity and nobody has any difference in the world. And I think we should also celebrate some types of differences. But I think economic inequality is, in my eyes, the single biggest issue that we have in the world right now. A lot of issues fall from that. If certain minorities would have more economic equality, they would be better off, I think. We'd have less racism, less sexism if people of color and women had the same financial equality as men do, statistically speaking. And so I think economic equality is a big part. Like a lot of wars get started from that. A lot of genocides and so many other issues happen from economic inequality that it's a really tough one. Now, should it only be productivity times equality? Maybe not. Maybe there should be other things like sustainability in there. So in the simulation, you have trees. The trees will eventually regrow, but you can have sort of a tragedy of the commons situation where all the agents just get rid of all the trees and then there are no more trees. And they all optimize their thing. Everybody's equal, but then like long term, everybody will suffer because there will be stasis and people won't build anything anymore. and it'll flatline because they destroyed all their resources. So I think sustainability is a reasonable one. And then there are interesting questions. Clearly utilitarianism isn't like I think at least philosophically the only answer to this. So you may need to have other like protections in the objective functions and sort of boundary conditions. We could talk about just that for hours probably, and over drinks in an evening we could really spend a lot of fun sort of philosophy and ethics of what we should optimize. I think what I'm hoping to realistically though is that when a politician in the future would say, I want to help the middle class. That's one of the things I want to do. And then eventually, either right away during their campaign or later on, they propose to say, now this is what I'm going to do this. And then you run that setup through the simulation and you say, that is really different from any of the potential solutions that the simulation would get for helping the middle class. Why does yours differ so far? What's your thinking about that will actually help more than these other ways? And so hopefully we can agree more easily on the objective function, and then we can disagree less on how to exercise and how to get there.
In your simulation, was there any emergent behavior that surprised you? Like, is there anything kind of counterintuitive that you discovered from doing these experiments?
Yeah, there's definitely some things that at first you're like, wait, this doesn't make sense. So we have taxes and we have subsidies. And when you look at it, it's actually the lowest income bracket got taxed a lot. And then it actually went down for the sort of middle class of the simulation. And we're like, wait a minute, that seems very counterintuitive. But it turned out they were also getting more subsidies. So they actually net, they were actually much more positive because the subsidies were also given to that income bracket. But that at first was kind of counterintuitive. But then once you double clicked on it and you realize, well, effectively, they're actually getting more subsidies than they have to pay taxes. So it kind of leveled out and made more sense.
Interesting. And sorry, I guess this may be a personal question, but you grew up in Eastern Germany, didn't you?
I did for a couple of years. Ethiopia for 3 years and 4 years or so of East Germany, and then Germany reunited. Yeah.
I see. Do you feel like that gives you a different perspective maybe than Americans on these topics?
I mean, I think I was still pretty young when the Berlin Wall came down, and so I think though culturally, of course, East Germany still had, it wasn't like Germany reunited and then there's like no more differences between East and West. In fact, some of the issues you see in other countries, like you would see between East and West, like the East still has lower income compared to the West, and a lot of women actually left East Germany to go to the West. So there are a couple of counties that have like too many men, and so on. So there's still a lot of differences between the East and West, still to this day. But I think, sort of growing up in Germany overall, which is where, the time I got most of my education was in reunited Germany, probably did affect me. Like in general, as I grew up, it was like free healthcare and free education all the way down to or up to a PhD level, master's level, was just not ever a politicized question. It was just a given. And being sort of anti big military intervention was something that was still pretty deeply ingrained in Germans, having, been there twice for a century. It was clear that that's something we should all try to, as best as we can, to avoid. So there's a lot less sort of pro-military conversations going on in Germany. And so it's kind of interesting. The whole political discourse in Germany has kind of shifted. Even the most sort of liberal, pro-economy, companies types of parties and on the political spectrum, none of them would ever question free healthcare or free education, because statistically speaking, it just helps everyone. And it's kind of an interesting definition of freedom. Even, is it more free that you always have healthcare no matter what job you have, or is it less free because you have to pay for it? Like, it's interesting cultural differences. So that definitely had a little bit of an impact.
Got it. Yeah, that makes sense. I mean, I guess I also want to make sure we cover some of the other papers that, since I have you, I'm just like I have so many questions. I was wondering if you could talk about. We've actually been, my company's been working with a lot of people doing various aspects of kind of protein generation and folding, and I really feel like there's something going on in ML right now with all the applications, and it's something I know very little about because it was didn't feel like a topic when I was in school. I'd love to just, if you could just describe, I mean, it's such an intriguing idea that language modeling techniques could be used for protein generation. Maybe you could just tell us what you did and kind of what you think about the field in general.
Sure, yeah. So generally, high level protein generation, or the ProGen model that we published, is a language model. What's a language model? It's basically just trying to predict the next word in a large unsupervised text. So you take all of Wikipedia, all of as much of the internet text as you can, and some people innovated by taking Reddit data, which is kind of more interesting, but then also has issues with bias and so on. And you have a very simple objective function for a large neural network architecture, just try to predict what the next word is. And people have been doing that for many years, almost many decades, because it's a very helpful way to disambiguate words that sound the same, but actually are written and mean something different. So if I want to say the price of wood versus would you tell me something, then the would sounds the same in both sentences, but one, it's the wood of trees, and one, it's the auxiliary verb. And so you basically want to disambiguate, like, which one is more likely in that context. And so that was used for speech recognition, and still is in a lot of speech recognition models. For translation, you can try to generate a bunch of possible translations for, a German to English translation, but then try to identify which sentences are the most fluent sort of for the English language. And so the sort of interesting novelty that came out recently with GPT and OpenAI is to actually take these existing models, make them even bigger, and then not just look at the perplexity numbers going lower and lower. Perplexity is essentially sort of an inverse metric of the probability that you assign to each word. So the less perplexed you are, the more correctly you've assigned probability mass to the word that actually comes next. And so as the perplexity reduced more and more, it crossed a threshold. And OpenAI was clever enough to realize the threshold is so low now, we should really look at what they're generating and see what comes out. And it turned out that they're actually surprisingly good, better than most anybody in the field had thought 5-10 years ago, in generating fluent paragraphs that actually made sense, that had some coherence and flow to them. And of course, after one or two paragraphs, they will repeat themselves, and it won't make that much sense still, because they don't have, this is, I think, actually an interesting question for the future. What's the next objective function? Like, just producing the next word and generating the next word doesn't include the fact that usually when you try to say stuff, you have a goal in mind, to convince somebody of something, to learn something, to get a message across, to get somebody to do something, all these different goals that you have as you try to use language. That, I think, will be the next level of AI research, to identify and understand new objective functions in general, and then actually allow AI to come up with its own objective function. But that's, anyway, so back to ProGen. So we have, this is fun. This is usually I don't have that technical of an audience to geek out about these things. It's just I have to stay a lot more high level for most other interviews. And so what's cool about ProGen is we took this idea of predicting the next word, which for languages makes sense. Humans can do it, but humans can't actually do it for proteins. We're not built to look at, the a bunch of different amino acids and protein sequences and then try to learn what they would look like, what would come next. And so I love the fact that when you develop really novel AI techniques, that you can apply it to so many different areas. And I still think that sort of one of the most exciting things is if you find a new model family and then you apply it to all these different things and you show, and eventually have a multitask model that can do multiple different things. And so here, it made sense to us because, again, it's a language that has a meaning. We just have much harder way of accessing that meaning. And we have a ton of training data. Now that sequencing is getting cheaper and cheaper, there's also an interesting sort of learning about, the first time somebody got sequenced, it was incredibly expensive, and that was like a white man. And now, you can, for $100, anybody can sequence their technology. So that's actually a great great story for technology. So long story short, we predict each new protein one at a time, and then we can generate new proteins. And so what does that mean? Why would that be useful for people not familiar with proteins? Everything in life is governed by proteins. Every function in your body is governed by proteins. Deep down in the level below cells and everything, it's all guided by proteins. And so digestive system, even you could develop proteins that will fight certain types of cancer, certain types of viruses. It's actually something we're also working on now to try to do some interesting things for curing certain kinds of viruses, but it's too early to talk about it right now. It will take some time. It's kind of another moonshot. But there's a really exciting work that you could do. You can even develop proteins that will eat plastic to try to help with pollution. Like this is unlimited the kinds of stuff you could do with proteins if you understood that language well. And so one big important factor for this protein model was that it's also a controllable language model, that it has these control codes in the beginning, because you don't want it to just sort of randomly generate random proteins. You have an actual goal in mind, like, oh, this should bind to this binding site in a cell, or this should, try to be able to connect to like a plastic, or all these different kinds of things you could do. And so we have these control codes. They basically give you the function and which area of the body and things like that it's in, or what other binding sites it should have. And then it will actually generate reasonable proteins. And Ali on our team has just been doing a phenomenal job pushing that line of research. And he's also the first author of ProGen.
Cool. So, I mean, how did you get the training data for that? Like, I could see how you could get like protein data from DNA, but how did you get the data of like what these proteins do and things like that?
So we took a subset of data and that had some kind of metadata associated with them. And what's interesting is there you actually can look at a lot more training data once you just say, look, any control code goes. It just goes in here, and then we can also use that. The majority of data sets are still very unstructured / there's no good sort of what's the word I'm looking for? Documentation and coherence between these different data sets. Each different data set, the proteins have different lengths, and then some people say, oh, it has like these 3 functions, and other people say, well, I just got this from somewhere. The next level is actually to try to train it even if you have 0 metadata associated with them. There are some interesting meta studies that just have a lot of unsupervised sequences from like soil and all kinds of things. And so if you could learn from unsupervised sequences, you could train on even more. But for now, we just took data sets that had at least some kind of metadata associated with it, even if there's no general nice sort of ImageNet-like taxonomy or WordNet-like taxonomy for them, but any kind of metadata was enough for us to incorporate the data into the model.
And was this the same with like GPT, where it's just like predicting the next one, and you're just trying to like have the lowest perplexity or like the highest probability that?
Correct. That's right. It's a super simple objective function still, and it's just trying to predict what's the next one. And what's amazing is actually that we and we just released this on Twitter today and on the blog post. We analyzed it, and some super fascinating stuff. So there's sort of protein folding, which is computationally really expensive. It's a really hard problem. But what we found is that even though the model goes through sequences, just one at a time, you can visualize the attention mechanism inside these transformer networks, and the attention mechanisms actually have a very high correlation to folding patterns in 3D. So wow. The areas of the protein, when they fold around and they actually are close to another area, and they would often fold in a way that they're very close, and then also different binding sites and so on, they're highly, highly correlated with transformer attention. So I think there's a lot more there to find out and explore.
And were the same mechanisms like attention that make language models work well? Was it the same things that really mattered for the protein prediction, or was there any difference in the kinds of models that work?
So to be honest, these models are so large, and we don't want to burn through like $100 million to train 10 of them. We just trained like a tiny samples of a transformer, and then we trained very, very few, 1 or 2, of the 1.7 billion parameter with 230 billion, 17 billion or so protein sequences.
I see.
So yeah, we don't have a huge ablation table where like we spend $100 million on not one piece of paper that gives all the different numbers on a big table. These models are so large, you really better not have a bug in that in the beginning and then realize it a month later.
But I guess, do these larger models work significantly better than like simpler models?
For sure. Yeah, this is really where neural networks shine. They have so much more expressive power. They can capture so many more different non-convex, highly complex functions that you need that. I think this is sort of where you couldn't do this thing with a linear model. Like the world is not linear. If it'd be a lot easier to solve all kinds of issues in medicine and so on if everything was like some nice convex problem in biology, but it's far from that. So we really need the complexity of these very large models.
Do you have like any way to, like, I feel like GPT-2, one of the coolest things about it was it produced these sentences where they're so evocative, and you kind of have the sense of like, okay, this thing is not good at long range dependencies, but it's very fluent, like, is there any, like, could a scientist look at the proteins you generate and have some sense of like these seem fairly realistic, or is there any way to measure that?
It's super fascinating, right? Like, what is the energy landscape in this discrete, protein space that actually makes sense? When you look at, so biologists already do this. Like 2 years ago, I think the Nobel Prize in Medicine was given to a team that essentially randomly modified existing protein sequences and then just tested them out. You can synthesize them and see if they actually have certain properties. Like you can try to make them fluorescent or not, and then see like how many proteins can I randomly change to still have that property, or have even more of that property, which could be useful for drugs and drug development and so on. And so you don't want to steer usually too far away from it. And then there are a couple of different metrics you can look at of like, as you generated a new type of protein that doesn't yet exist in nature, how likely would that to be structurally sound at all? So, and we actually, in the paper, we have different experiments where we show that there's a certain energy that, like, with programs that you can compute that says like this would actually have a very low or very high energy, and hence this protein would not just disintegrate and fall apart. It would actually be structurally sound. And it turns out that compared to the random baseline, which is relatively easy to beat, we're so much better and create much more stable proteins that are more likely to actually work.
That's so cool. All right, I'm going to keep jumping around because I have so many questions I want to get through. But I'd love to hear about the language model that you came out with last year, the CTRL, and like kind of what inspired you to make a new language model, and like kind of what it does like differently than other options out there.
Yeah, it's a great question. So control is essentially a controllable language model, where instead of just saying, here's a beginning sentence, now just spitball, like randomly generate like how that could continue. Usually it would make more sense for us to try to create language technology that we have a little bit more control over. So we created these control codes that essentially say, for this sequence, but also given this genre, like continue the sentence. So if you start with a knife, and you say the genre is a horror movie, then like the knife peeked through the door and blah, 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 crazy stuff is happening. Or if you say a knife and a review story, then it's like, oh, the knife cuts really well, my vegetables, my husband loves using it in the kitchen, and blah, blah, blah. So that's kind of a difference. You have more control over what it would actually generate. And then the control codes can also be used as task codes. And you can say the task code or control code is generate this translation of this, and then it sort of generates the translated sentence after, instead of just sort of the next random possible sentences that might make some sense. And so at that point, and this has been something I've been trying to work on for a long time with DECA, the natural language processing decathlon, DECA NLP, and a lot of other projects, is I think we're at that state now in NLP where we can try to just solve a lot of these standard NLP problems with having a single large multitask model that you have the substrate, a large complex neural network structure. It almost doesn't matter anymore these days what it is. Like you could probably have a very deep, large stacked LSTM. Now it would be a transformer. will probably come up with other versions of that, but it's some kind of large general function approximator, some neural substrate. And then the novelty is you try to train it to have all these different objective functions, different tasks. It gets better over time. And then you can get to transfer learning tasks. You can get to zero-shot abilities, and so on. So that's been a dream of our first line of that work with Brian McCann on contextual vectors, COVE, which we trained back then still with translation. Then Elmo took that idea and replaced translation with language modeling, which is even more clever because you have even more data that's unsupervised than you have with translation, even though that's sort of the biggest supervised data set like ImageNet. And then Elmo, of course, became BERT with even more novelties on top of it, but still sticking to language models and taking these contextual vectors. And so when you have contextual vectors that can get easily fine-tuned on multiple tasks, then you have something like Deca NLP, where you have everything as described as one task. Then you get closer and closer to that step to eventually just having a single model for all of NLP. And then my hope is that eventually the NLP community can work in a agglomerative, kind of cumulative way, where we have a control-like language model or question answering model that you can ask any kind of question and so on. Or you can even have just a general language model, but you ask it questions and then out comes, the next words that come after the question should be the answer if it really learned something about language and the world and everything. So there are these equivalent super tasks of NLP. But long story short is if we're able to do that, and every research that we do actually makes an assisting supermodel better and better, then we would all of a sudden have an explosion, I think, in progress in natural language processing. And we would stop saying, oh yes, this paper has a baseline and we're making it a little bit better. And then the next paper, we jump back to the baseline, we make it a little bit better in a different direction. The next time we improve our baselines from time to time, but all these papers do sort of one-offs improvements of these baselines versus every time somebody publishes a good paper, the model overall gets better, and then everybody will start directly from that improved model. So that's been my dream for the NLP field for a while.
It does kind of seem like NLP's moving in that direction, doesn't it? With like the big like multitask baselines.
That's right, and T5 and all these other large models. I'm super excited to see it. I think it's finally happening. It'll still take some time because just like in about 10 years ago, I had my first deep learning neural network paper at an NLP conference, and the reviewer still wanted to reject it. There are a lot of people like, why are you applying neural networks to NLP? That stuff from the 90s, it doesn't work here. And I had in the beginning of my PhD, a lot of papers rejected. And I think part of it is that a lot of people have built their careers and their knowledge and their academic standing and so on feature engineering. And so when you say, oh, you don't need to do feature engineering anymore, you just now have these models and they learn the features, it doesn't sound that great if you've done feature engineering for 10 years. And now we have the last 10 years or so of people doing architecture engineering. And they don't want to hear that the architecture doesn't quite matter anymore. It's now about the objective functions. And so let's ignore all these architecture engineering papers. Let's just assume there's one very large, efficiently trainable neural network architecture, probably a transformer because it's parallelizable on GPUs nowadays, but it could be LSTM, whatever. And we train this really large one, and now we become clever about the objective functions on improving that neural substrate. Again, it will be a shift, and it usually takes the community a couple of years to make these shifts, and young people are jumping on it, and then people that are older and have been longer in the field will eventually kind of through their grad students and so on adjust and then embrace it and then start doing amazing work in that new area.
So how does control fit into that? So is that it sounds to me like, was that a new architecture or was that really just adding control codes?
It was mostly adding control codes to a large language model. That was kind of the main idea. And it fits into this as a way to unify. Basically, the way I see it is there are three equivalent supertasks of NLP: dialogue systems, language models, and question answering systems. You can cast every other NLP problem into any of those three, and you can map those three between one another, right? Like in a dialogue, something happens, and then you have to generate the answer to what the previous agent just said. And in language modeling, you you can also cast it as question answering, right? Like asking a question, and then the words that should be predicted after that question should be the answer. So question answering and language modeling are equivalent. So we tried this with Deca NLP, where we had language modeling, where we used question answering as that default framework. And with control, it's the acknowledgement that if you start with a large substrate that can be trained unsupervised from a large amount of text, it's like sort of the best single task to then transfer from and do multitask learning from.
And do you treat the control codes like differently than other like tokens? Because I feel like I see a lot of like examples where people, like they do a translation by just showing pairs, and then it's like, oh, their language model starts generating pairs. Is that the same thing, or is it somehow control doing things more systematically?
So you do have, in some cases you can actually make those control codes be language themselves, right? So you could say like, here's a question, now is a text, generate the answer after you read that whole thing. But you can also have control codes that are just like task _1 is a control token.
Right.
And then what's surprising is with these control tokens, the outputs will be very different, right? Like translation, all of a sudden generating a very different output with the same neural network architecture overall. It's pretty amazing that works.
It's amazing that works. I mean, I can't believe that works. Like I remember when I was studying this stuff, it was like, it was like linguists that wanted to do it completely explicitly and rule based versus like, people doing machine learning. So I guess we sort of keep going up levels of abstraction.
It's interesting. I sometimes these rules I used to just so much discard it, but when you try to build a real system for a real company, you have a chatbot, and and that company has in the end like everything. If you have the ability to make it into chatbot, you have some API somewhere, right? Whether that API is like you click on these fields or you already have it as a program, it needs to be a structured, disambiguated programming language output at some point that fulfills actions. Like, what order do you want? We go into our order management system and upgrade, this field and resend a new one that goes again to some logistics center. And so when you have these concrete chatbots for a company, I was always thinking, oh, it should just all be learned, and then at the very end it generates some code and so on. But the truth is, companies want to sometimes have control. They want to say, yeah, maybe there was like bad biases in my past training data, or maybe we changed the process and now we don't want to do it the way we used to do it. It's going to be a new process. Or like in this country, we have some regulations, so we need to first ask this other question that wasn't in the training data from that country, and so on. So man, I'm surprised how often when it comes down to like real business and products, you have to still have these rules in there.
I'm curious, actually. So you've gone through this transition from like mainly academic to like startup founder to kind of like big company, like C-level executive. Has there been any other surprises like that? Like kind of seeing how businesses think about machine learning versus how academia thinks about it?
Yeah, one thing I love is that I still dabble a little bit in all the other ones, and obviously we're still doing fundamental research now, but also a lot more product and stuff. But there are a lot of interesting different mindsets. In many ways, if you have a domain problem, this is actually something you see even in research. If you work in just biology, or you're just trying to solve one particular domain problem in a particular modality like language or vision, then it's rare. It's really hard for the people working on those applications to also find out new architectures. It's just a different mindset. You're trying to solve the problem. Like if you try to, for instance, help babies in the ICU, or you try to like cure COVID or something, you don't care. If you can do it with naive Bayes or an SVM, or some like latent Dirichlet allocation, or whatever the hot like model used to be, the popular model at the time, it doesn't really matter. You solve, like cancer or some or specific type of subcancer. And so it's interesting. You're just starting to throw the kitchen sink at applied problems. And that's sort of still true even for applied engineering teams. They say, by the end of this quarter and this sprint planning and so on, you gotta have a solution that works on some level. Whether it's like the absolute latest, greatest, and like really squeezes out those 2%, that depends on the business model. Like for Google, it makes sense to spend a lot of time on AI because they have clearly certain AI metrics, like recommender systems for advertisement and so on, where an improvement in an AI metric results in immediately more revenue. That isn't the case for every AI problem and solution and product out there in the B2B world. Sometimes it's just like, if it kind of works, you make the same amount of money than if it works 5% better.
What are the things that Salesforce cares about? Like, what are the ML applications that are really important inside of your company?
So there are a ton. There are roughly different groups, such as like sort of packaged applications that you can sell as is, like a chatbot application or opportunity or lead scoring. Some of these sometimes go into a second category, which is sort of quality of life in the user experience, where you just kind of make the product a little bit better, and we have a lot of those.
Wait, sorry, what would that be like? Like, make the product a little better?
So, for instance, you type in the name of a company to create a new lead object as a salesperson, and it just like finds the company logo, just like boom, and now it looks better in a nice table. This is like not a feature you could get money for. Or the search functionality. Search is like one of the most used features in most CRM software, but making search like spending another $1 billion on improving search is like questionable, like, because you make the same amount of money, everybody assumes searches just kind of work, and you don't pay extra for it for the most part. And so so you have packaged applications where you clearly make a lot more money, like a recommendation engine in Commerce Cloud. We're one of the largest e-commerce platforms in the United States, which many people don't know because nobody goes to Salesforce.com to buy their shoes, but you go to Adidas.com, which runs on Salesforce. So there you have recommendation engines as clearly like sort of almost an obvious kind of task. Everybody knows you should use recommendation engines in e-commerce. But those are sort of packaged applications that you can sell as is. Then you have these quality of life features. You have things like you want to improve your operational efficiency, like make recommendations for your own salespeople, or learn how to work with your data centers more efficiently and things like that. And then we have in the company also a lot of platforms. So where we enable our hundreds of thousands of customers to build their own AI applications with their own data without us interfering. And so there you also have interesting problems, because you have to not just build one app, but you have to build an engine such that a lot of admins and with low or no code, you can create an AI application, some prediction model, some recommendation model, some OCR model to read in forms from some complex form, boom, directly into digital form, which is surprisingly still necessary a lot of times these days. So there's so many different applications. That's kind of why it's so exciting here.
How do you even, like in your team, how do you pick what to work on?
It's a complex process.
Driven by research interests?
So I'm wearing these different hats. And so on the research side, we go mostly for impact on the AI community as a whole. And so that's one of our objective functions, just impact in AI research. Another one could be impact down the line eventually on products. So we have things that we work on in medicine where we don't currently work in medicine, but maybe down the line that could be used. We have things that we work on in the AI Economist or ProGen, where maybe eventually the world will improve, but it's not really clear. So there's sort of pure AI research impact on the world and all our stakeholders in the community and so on. Then on real products, so a lot of natural language processing research is surprisingly close. Like you can do some fundamental research in semantic parsing, learning how to really disambiguate a sentence into a query that could be used to get the answer from a database. And that is fundamental research, but it's also pretty applied and could be used for Tableau and a lot of other exciting areas inside the CRM where people need to find answers in a database. So that is kind of the two different worlds on the research side. And then on the product side and the large engineering groups, it's very customer driven, and sometimes it's driven by what we think the future will be like. So we announced, for instance, at Dreamforce last year, a first agent over the phone. So like a kind of agent that you can just pick up the phone and have a natural conversation with. So Mark and I were on the keynote stage and showing sort of what that would look like. And so that is obviously something that maybe customers aren't even thinking yet about. They're like, because they're not sure it's even possible, but we're working on those kinds of things because we think it will be possible soon. And we're now, yeah, making it possible.
Cool. All right. Well, we're running out of time. We always end with two questions that I didn't warn you about, but I'm kind of curious what you'll say. So, so the first question is, like, what's something, an aspect of machine learning that you think practitioners are not paying enough attention to?
I think now that AI has reached that deep impact level on the world, we really need to think about the biases in a holistic way, like the systems, the people, the structures that are using AI for something. Are we thinking enough about the bias? And as AI has a bigger and bigger impact on people's lives, I think the bar needs to increase more and more. Like a loan application AI that decides who should be able to start a business and so on, you really need to pay a lot of attention to the biases in the data sets, the biases of how those data sets are created by the people, the sort of hidden agendas, and what the status quo is, and so on. And how do you improve the world in the end versus entrenching it in the current system and just keeping the current system the way it is. And I think that's sort of something that a lot of practitioners still need to work on, and now also more researchers need to work on, because even when we play around with like, oh, this is just a cute little artsy research project, right? This depixelization, it actually is, like, it turns out it's like another deeply rooted bias that is there and that gets exposed in that, and that I think we should all work on a lot more.
Do you have any suggested like reading material or for people who want to get more educated on the topic where you'd point them?
Yeah, for sure. I think that Timnit Gebru right now is really one of the leaders in that area, and she has given this great tutorial at CVPR, and the slides are online. There are a bunch of papers from a lot of other people. At our team, we also have Kathy Baxter, and she's sort of looked at more of the applied side of AI a lot more, making sure that AI systems are explainable, transparent, that you have feedback loops in them, that people can give like feedback to when an important decision about them was made in an automated fashion. They think it's wrong, that they're able to fix it and sort of escalate it to humans or improve that data. Making sure they're explainable, you actually understand how it came about that this decision was made about you, and so on. So there are a couple of different things, like making sure, even sounds kind of crazy, but I think we need to even think about human rights when it comes to AI applications that we work on. And so I think Kathy Baxter has a lot of materials online, interviews and materials. We have some trailheads also on Salesforce, the Salesforce learning platform, on ethics and ethics in AI in particular. And then Timnit Gebru has a lot of great materials on research in AI and the systemic issues as well as sort of other concrete issues.
Cool. Yeah, we'll put this in the notes and totally agree. The final question. So you're coming from kind of a research perspective, but you're at a company that does lots of applied machine learning. When you look at that path from like taking like a research thing to deployed inside the Salesforce product, what's like the biggest challenge that you see in that process? Like, where do things get bogged down the most?
Boy, it's interesting. We have actually, I feel like we're finally really getting into a groove, and we're getting a lot of features out much more quickly than we used to. And I think part of it is just that the two different sides of like the pure researchers slash research engineers slash data scientists slash sort of data engineers, they have a certain way they see of where's the complexity of deploying an actual AI product. And then you have engineers, and the truth is, though, that somewhere between 5 to 20% of an AI product is actual AI. And then somewhere between 95 to 80% is just relatively standard, but still very hard software engineering. And, like anybody can nowadays quickly hack together a quick, like, TensorFlow image classifier, right? It's like, oh, and you feel like after 10 minutes, you're an AI expert and so cool, and you're super smart and you know AI now and so on. But then when you actually want to deploy that in a large context, now you have load balancing, you have security, you have privacy, and you have all these issues. Now somebody from GDPR from Europe says, I want you to delete this picture. Now you need to retrain it. If that happens every day, are you retraining a whole huge model every day because somebody you're asking to take that training, their data out of the thing that eventually fed your classifier? How do you update the classifier continuously? How do you make sure that as you update the classifier, if you've had something like FDA approval or HIPAA compliance, how do you make sure that like the new classifier is still compliant with all the various regulations you have? So there's so much complexity on the engineering and productionizing of AI. And that is sort of what a lot of people who are super deep AI experts often underestimate.
Cool. Well, great answer. And great talking to you, Richard. Thank you so much for doing this.
Pleasure. Great questions. Yeah. It was super fun to geek out a little bit and go deep into some of these papers.
Totally, yeah. Thanks so much. When we first started making these videos, we didn't know if anyone would be interested or want to see them, but we made them for fun. And we started off by making videos that would teach people. And now we get these great interviews with real industry practitioners. And I love making this available to the whole world so everyone can watch these things for free. The more feedback you give us, the better stuff we can produce. So please subscribe, leave a comment, engage with us. We really appreciate it.